So hello everyone, thanks for joining, and also hello to people that will see this video or think. I am Meir Benayoun, staff backend engineer at GitLab, and I will present today the first part of the OCaml workshop. We will talk about functional programming, OCaml, a bit of chess, and static analysis. So just before starting, most of the presentation will be only a lecture, a bit of hands-on today, but most of the hands-on will be the participation to the chessboard contest. So if you have not prepared the prerequisite to install OCaml and everything, if you have, you can play around during the presentation. If not, you can just enjoy the lecture and continue with the hands-on exercise later. We have a 2 hours session today with a small 15-minute break in the middle. And at the end, I will talk a bit about how to participate to the chessboard contest. If you have any question, if it is related to OCaml and functional programming, you have an issue for that. And if it is a technical issue for installing things, there is also an issue for that. So feel free to ask any questions there. I will answer later. Okay, so I love starting a presentation with a bold statement. So this is my bold statement. This presentation is only my vision of functional programming, and if you will ask another OCaml or functional programming expert, probably you will get a different story. So this is my vision, and you can agree or disagree with that statement, but what is important is at the end of the presentation, I hope that I will be able to share my vision with you and to give you a bit of understanding from that perspective. So formal methods is the future of programming, and functional programming is only a step to that future. So I said that this is a subjective presentation, my vision of the things. So a bit of background about me. I started a long time ago software development, almost 10 years in imperative programming. And at some point here, I discovered what is functional programming and OCaml. I thought that I knew almost everything about programming and software development, but here is you have a picture of me 20 years ago, so you can see that I was surprised.
Meir, I'm not sure you're presenting your screen.
You don't see my screen?
No, we don't.
Oh, so I will start again. Sorry for that. Thanks that you told me now and not at the end.
Sure, no problem.
So just a second. Okay, so you should see that now.
Yeah, we see it now.
I'm just coming back to show you the slides. Timeline, we talked about that. There's a bold statement about functional programming. And so here you can see there's a nice graph with my 10 years in imperative programming and the nice photo of myself surprised when I discovered what is functional programming and OCaml. And so from this point, I really enjoyed this new world that I have discovered in functional programming. And so I started to learn more and more in that area. And I discovered that it is not only the surface of a new programming language that I have discovered, but it is a lot more. And I would like to share a bit with you in this presentation, not only about OCaml itself, but to have a higher perspective about this whole world. So you can see here that I started with OCaml and I climbed to Coq. You can see Opalang. Probably you don't know what is Opalang, but it is still in the map here. And with culminating point here with my PhD thesis, which was written 100% in Coq. And I will tell you a bit about Coq after that, but I think it is the next level of functional programming. And after that, I joined a well-known application security company where everything was written in C#. So you can see it was a bit shocking for me. And in the last years, I am trying to climb again this mountain. And the GitLab Advanced SaaS, I am really excited about it. It is it is part of the journey. Okay, so we have a pretty busy agenda today. A lot of concept to review. So sorry for that, we will not be able to deep dive into everything, but it will be a short explanation of each and every concept. And you are welcome to ask any question if you want to know more about this topic in the dedicated issues. So we will talk about functional programming principles, a list of things that we will explain. And I will share with you my vision of static analysis and formal methods and how it is related to functional programming. And on the right part of the screen, you can see part 2 and part 3 for future sessions in a few weeks. We will have the chessboard contest, where each participant will be able to implement in OCaml a chessboard, and we will have a contest with great prizes that you will be able to win. And also one of the goals is to learn from each other, to have a live code review in the session, in this session. And the last part, after we know more about OCaml, we will have a deep dive into the internals of the SaaS engine of the GitLab Advanced SaaS. And we will see high-level architecture, and also we will show a bit inside the code. And all this presentation is hopefully the starting point for involving more people into the OCaml projects that we have, in particular the GitLab Advanced SaaS. So let's start. Okay, you probably know what is a Turing machine, and it is always presented as the basis of computation, the theory of computation, the foundation of computation. And it is really nice to see that a simple machine like that can express everything that is computable. But it is only one side of the story. And the Turing machine, as I see it, is the basis of imperative programming. But almost at the same time, the Lambda calculus has been invented by Alonzo Church. And the Lambda calculus is the basis of functional programming. And what is interesting to notice here is that they managed to prove that the expressive power of both approach are equivalent. So the Lambda, any programming language based on the Lambda calculus is also Turing complete, and vice versa. So it is a very interesting point. But from this starting point, we have the history of the Turing machine. If you know a bit about the Turing machine, it looks like a memory. You have a tape with cells, and every cell has a value, and you can move right or left in the tape and change the values. So it looks like the ancestor of assembly. And from assembly, we get C, and from C, we get C++, and so on. And if I take a look at C++, I'm not sure we took the right path in the history of a programming language. So let's present the second part, the Lambda calculus, as also its own history. What is very nice with the Lambda calculus, I think, it is a very simple way to define a language. You have only three things to define the Lambda calculus. You have variables, just names. You have Lambda abstraction, which allow you to, we can say, create a function, but it is only a syntactic representation with the symbol lambda. X is the name of a parameter, and E is any expression in the Lambda calculus. So that way, you can say that we have a function that takes one parameter and gives the value of the expression when you replace every occurrence of X by its value inside E. And the third thing that you have is the application. If you have a function, a Lambda abstraction applied to a symbol A, so you can do the replacement of A inside E. Every occurrence of X will be replaced by the value of A. And so this is the application. Those are the only three parts of the syntactic definition of what is a Lambda calculus. And from that, you have a rule called the beta reduction. And this rule explains how to reduce an expression. You can construct a very big expression with a Lambda calculus, and you will reduce it until you get a value. And so the beta reduction explains how you reduce your expression into a value. You have two examples here. One example is a function that takes X and returns X plus 1. And this function is applied to the argument 5. And so how can you reduce that? You simply take 5, and inside X plus 1, you just replace every occurrence of X by 5, and you get 5 plus 1. And then you can reduce it to 6. You can object now that 1 is not defined in the Lambda calculus. Also 5 is not defined, and also plus is not defined. But if you learn more about Lambda calculus, you will know that only with those three things, variable, Lambda expression, and application, you can define almost everything. You can define natural numbers, you can define all the operation of natural numbers, and you can define every possible data structure and so on. So it is a basis for any high-level language that you will construct on top of it, and all the features that you will add in your functional language will be only syntactic sugar of Lambda calculus, just to make it easier for the human to read it. So you can see the simplicity of Lambda calculus and also the power of the Lambda calculus, because you can compute every computable thing with these simple rules. Another example here, I would like here to jump to VS Code just to show you how we can do that in OCaml. So let me share. Okay. Okay, can you see now my VS Code?
Yes.
Great. Okay, so now I am in VS Code. I have opened a new ML file, a new OCaml file. So we will write something similar that we have seen in the Lambda calculus. I will define a function. The syntax is a bit different in OCaml, but it is the same concept. Instead of Lambda, you write fun, x plus, it was x plus 1, I think. Okay. And we will apply it to 5. So now I will evaluate this function. Okay. I have evaluated this. And you see that I get the result 6. Okay. So this is a simple evaluation of this function. Now, just to let you understand what kind of syntactic sugar you can add on top of it, instead of writing it that way, you can define a name. But if you want to name something, okay, I will do another example. I would like to write something like let x equal 2 in x plus 5. Okay. So here you see that I get the value 7. But as I told you, it is only a syntactic sugar on Lambda calculus. So how you can define this kind of thing? Under the hood, it is this let x equals something in. It is only syntactic sugar on a Lambda calculus construction. And you can, if you want to name something, you can just define a Lambda abstraction with that name. A Lambda abstraction with that name. So you will have what you want to compute with this name here. And you give the value of the name. So this is equivalent to the line we have above, line 6. It is exactly equivalent. So this is easier to read for a human. So we define this kind of syntactic sugar in language, in functional languages like OCaml, but it is only translated to this kind of thing under the hood. So it is only a syntactic sugar upon Lambda calculus. Okay, so that's what I wanted to show here. So let's go back to the presentation. If I can find it. Yeah. Okay, so we are back to the presentation. You can see here the history I have written for Lambda calculus, and you can see here Lisp, OCaml. Actually, Lisp is closer to Lambda calculus than OCaml. OCaml looks like a high-level language, much more high-level than Lisp. And you have Haskell, and I think that one of the most beautiful example of evolution of Lambda calculus is Coq, and also similar languages to Coq. I will explain a bit later. So I think that even if it is not the mainstream of programming language, from my vision, it's a much beautiful evolution than what we got from Turing machine to C++. But that's a personal point of view. Okay, I will not read everything here, but a few important things about Lambda calculus. What is a function in Lambda calculus? We know how to define a function in Lambda calculus, but it is important to notice that every function are deterministic. You cannot write a function that is not deterministic in Lambda calculus. If you give always the same parameter, you will always get the same return value. There is no other way. You cannot do anything different in in Lambda calculus. Also, every function is total. If you give a value, if you give a parameter, you will get a value in return. You will not get an exception. You will not get, I don't know, any runtime error or something like that. It doesn't exist in Lambda calculus. Functions are first-class entities and higher order functions. Just means that it is natural to pass a function as parameter as another function and so on. There is no distinction between a value and a function. Everything is a function in Lambda calculus. And you will see that it will have impact in OCaml and in any functional language related to the Lambda calculus. Okay, so let's start with a very long list of principles that we have. So querying, it is very natural when you are based on Lambda calculus to, I don't know if you noticed, but in Lambda calculus, when you define a function, you have only one parameter. You cannot define a function with two parameters, but it is not a problem. You can define a function that takes one parameter and returns another function which takes another parameter and so on until you return a value. So it is only a kind of nested functions. And you have a simple example here, a syntactic sugar of OCaml. You define a function with two parameters, but we know that Lambda calculus don't have two parameters. In fact, you get a function. If you give it a x, you will get another function that will take a y. And if you give a y, you will get another. You get a value x plus y. So, for instance, you can define increment and apply add to only one parameter, and you will have a function that will take an integer and return you the next integer. Okay, so it is a very simple example, but you can do with this kind of thing with any function that you define in OCaml. So that's querying. Another very important concept is immutability. We have seen that we want deterministic function. We don't want side effects. We want that when you give a parameter to a function, you get always the same value. And when you don't need to have side effects and you don't want to have side effects, you can do many nice optimizations. And for instance, here you see that I define original list, which is a list 1, 2, 3. And I want now to add a new, an additional element in the list. I want to add 0. I cannot modify the list. What I can do is define a new list. So I define new list, and this new list is 0, 1, 2, 3. It doesn't modify the original list, and you can still use it. And you can rely on the garbage collector that will remove everything unneeded if you don't need it again. And one other nice thing that you have is memory sharing. If you know that you will not need to modify the value, you can share the memory. And instead of copying, having 1, 2, 3 somewhere in memory and 0, 1, 2, 3 another place, this is a representation of the memory. You have the original list starting here, 1, 2, 3, and the new list start here, 0, 1, 2, 3. And this part, 1, 2, 3, is shared by both lists. And you can define another list starting somewhere else and also sharing the same sublist. So also this is very important to keep in mind when you program in OCaml, that kind of memory concerns where you have nice optimization. Pure function, when you come from Lambda calculus and you go to a real language like OCaml, you still need to keep, you still want to keep the important properties of functions. That function will be deterministic and you will not have side effects and so on. So in functional programming, this is called a pure function. If you give the same input, it will give you the same output. And if you are doing side effects, and you can, OCaml, because it's not a pure Lambda calculus, you will do dirty OCaml. It will not be pure OCaml. But sometimes you want, for optimization purposes, you want to do side effect. And so how can you do side effect and still keep the nice properties of pure functions? So this is called referential transparency. The important thing is that from outside of the function, you have no way to differentiate if it is a pure function or not. It might have some side effect inside, but it is only a local side effect that has no impact on the program outside. And so I give it two examples here. Increment counter, just to show you how you can use references in OCaml for doing side. Doing a side effect here, but always start with 0 and just add 1. But sometimes it is useful to do that. So for instance, you want to define the Fibonacci function, and let's take 1 minute to go back to the VS Code so that I can show you. Okay, actually, I have. Is it okay? It is not the right example. Can I copy paste from here? No. Okay, so I don't want to lose time. We have a very busy agenda, so I will let you do it as an exercise later. Where is? Can you still hear me well?
I can hear you well.
Yeah, perfectly.
Yeah, great. I just seen a warning of unstable internet connection, so just ensuring. Okay, so this is referential transparency. You can try that at home. The important thing here to see is that you have side effect inside. The hash table is something that you can update the value of the hash table. But the important thing here is that from outside, if you give the same input, you will get the same output. And you have no way from outside to understand that there is a local side effect, a local dirty thing. Okay, another interesting example here. Also, you can try those example at home. You have here the definition of the Fibonacci function, very simple one. But you know that it is really inefficient when you start going with numbers like 10, it will just not finished. So you can say, okay, I want to memorize this function. If the function has been called before, I don't want to compute again on the same input. I want to store the previously computed values. And if I get the same input I already got before, I will give the output from the cache instead of computing again. So this is the memo function. The nice thing here with the memo function is that it is a generic implementation that you can use for everything. You can use it here for the Fibonacci function, but you can use it for any function that is taking any type and returning any type. So this is, you can see here the simplicity and the power of functional programming, where you can define a very simple function that is so generic. The only thing here is that Fibonacci function is recursive. So you don't want just to check if the first input has already been computed in the cache, but you want during all the chain of the recursive calls, you want to check for each and every input if it was already computed and then use the cache. And if you want to update the memo function to be recursive, and so that the memo function can take any possible recursive function that you define from any type to any type, this is the implementation. This is actually a very good implementation that you can use in a generic way. Okay, so recursion, just to notice that recursion is very important in functional programming because you don't want to do side effect. You don't want to update a value, update a variable. You don't have the concept of variable in pure functional programming. You cannot do, it is really less useful to do loops because it is not the correct way to compute something. In the loop, in order to be useful, need to update something, update some variables that you will be able to look at after the loop. So the natural way to deal with iteration in functional programming is recursion, recursive functions that are calling themselves. And you can see, for instance, factorial, or we have seen also Fibonacci, that is a very nice and pretty way to define a recursive function. One word about tail recursion. You cannot have infinite loop if you are not using loop. But what you can have if you are using recursion is infinite recursion, and you will you can go to Stack Overflow if you have too deep recursion. And a very important optimization in OCaml is that tail recursive functions are transformed automatically by the compiler, are optimized into a loop when they are running. So if you are writing a tail recursive function, you will probably not reach the Stack Overflow issues because the stack will stay at a very low level. Algebraic data types, it is one of the very important concepts in OCaml and functional programming language, and it is one of the concepts that is still present only in functional programming and you cannot find in most mainstream languages. And it is a very powerful one. Defining a type, you have two things. You have product type and sum type. You can define constructor of type, and then you can combine the types together in order to construct more structured type. So I will present product type. Product type is just a way to combine multiple value in a single value. For instance, you have a point. It is a record with two values. and you name them. So this is a way to combine two values into one. You also have tuples and so on to combine. So this the product types, you know that from almost any language. The sum type is a bit different. The sum type give you the possibility to have one value or another. You can a value of one type or a value of another type. It's like a union, but defined in a much much more formal way. So for instance, you have a shape that can be a circle or a rectangle. The circle is defined by one float, and a rectangle is defined by two floats. And so you can use those constructor in order to construct value of the type shape. When you have some types, you can destruct them using pattern matching. Another example of algebraic data type, you can very easily define the AST, the abstract syntax tree of a language. This is here a very simple language. You only have let bindings, variable, multiplication, addition, and integers. And you see here that it is very easy to define such an AST. And if you take a look at the internals of the static analysis engine, you will be able to see that it is defined in a very nice way, like this, just a bit longer, much longer. A polymorphism. We have seen this a bit, but I will tell a bit more about that. In OCaml, you have parametric polymorphism. It means that when you define a function, you can define it in a very generic way so that you can apply it to many types. For instance, if you define a function that takes x and returns x, so you have type inference that will infer the most generic type, which is quote A to quote A. It means that quote A is a type variable. So it means that you can give to ID a value of any type that you want, and the function will return a value of that same type. So for ID, it is very obvious, but you can do the same for much more complex function. And for instance, you have functions on a list. You have the map function, the fold function, and so on, that are very generic, and you can apply them to list of anything. So it is important for reusability, flexibility, and also type safety, because in many languages you can have this flexibility, but it is a compromise and you have less type safety. Here you have a very strong type system that give you strong guarantees about what is going on and that you don't have a type error. So why algebraic data type are so powerful? I will let you read more if you are interested. Just to say the expressiveness, it is really modular, and the pattern matching is a really powerful way to deconstruct the sum types. Yeah, type safety, natural representation of recursive problem. See, we don't have time to dive into that, but you are invited to read more about that. A very simple, a bit more complex example, but still simple, where we have defined the simple language here that we have seen before. You have an evaluation function that takes any expression in that language and will evaluate it to a value. And so this is an interpreter for the language that we have defined above. We have here the definition of the AST, and we have here the interpreter, the whole implementation of the interpreter. And you can see how concise it is, how nice and powerful. Why powerful? For instance, you can see that you have here the pattern matching. That is, when you get a value, you are it's like a switch according to the type of the parameter that you got. You will do a different operation, and this pattern matching, the type system, give you a guarantee that you did not forget any case. You have exhaustiveness checking in the type system. Okay. So for instance, you can see here this simple expression in the language that we have defined. And so this is the way it is represented in the AST. And here you evaluate it and you get the value 14. Yeah, one of the nice things I like is railway error handling. I will give you a link to the presentation. It was defined, I think, a long time ago, 10 years ago, something like that, when I read that. And I really love the way how it is explained to programmers that know what is error handling and know how doing it the nice way or not the nice way. Yes, I will explain shortly here, but I strongly encourage you to take a look at the video. I will give the link in the next slide. So here you can see that you have two functions, divide function and the add one function. Okay, but the divide function cannot be defined for any possible input. If you give y 0, you cannot do the division. So you need some way to handle this error. The way to handle an error is just to return a value. We don't want to use exception to break the flow. We just return a value. But the value that we return is using a sum type. So you can return an OK value or an error value. Actually, this is not something built in. You can define your own type with everything you want. You have the whole definition here of the result type, which is OK of some type or error of some other type. So this is the definition of the result type. And divide is just taking two integers and returning a result type with two parameters are integer and string, because the parameter of error is string. And add one is doing the same, taking one parameter, an integer, and returning an int result. So now that you have that, you can very easily combine those functions. For instance, divide 10 by 2 and add 1. So this is combining the two functions, and you get the result. The result here will be OK 6. If you do the same here with 0, and you want to add 1 after that, you will not have an error in the middle. You will just get the error value division by 0 at the end of the combination of the function, and still you don't need to take care of error handling here in this line. You just want to combine this function and this function. So let's do that. And it's really simple. You don't need to take care about error handling. The error handling is handled in a very nice way under the hood. Okay. So let's go on. This is a bit more complex example of error handling, but the exact same concept here, where you can see you have the same, the exact same code here and here. Just the first value is different, and the error handling is handled inside the combination of the function. So you will get here an OK value or an error value, and no matter where the error occurred during the combination, we know how to combine the value. So here is a link to to the presentation I talked about. He's explaining it in a much better way than I do. So I really encourage you to see this video. And so now let's talk about monads. I keep that for the end of the presentation, at least for the end of the functional principles part, because it looks scary. If you are looking at, you are Googling what is a monad, you will probably get something like that. It is just a monoid in the category of endofunctors. And it is correct, and it is very nice, but it is not really useful if you want to understand in practice how we can use a monad and understand the concept without learning all the theory in mathematics. So let's explain it in a much simpler way. So what is a monad? A monad is just a way to wrap a value. You are wrapping a value and you are creating a second world. So I will try to explain it simply. You have two constructors. You have a way to just return a value. You just want to wrap a value inside the monad. And you have another operation, which is bind, when you want to combine functions in the monadic world. You have a few laws for the monads. You have the identity, right identity, and associativity. I think it is. I don't think it's so important to understand here. But if you take a look at this, it is just what we have seen before. The return and the bind operation. If I come back here, the symbol I have defined here for combining two functions, that when you are combining return and the subtract and the divide and so on, this is the definition of the bind operation. So here you define a type, and the type is actually the definition of the monad. And here you define the bind operation that helps you staying in the monadic world when you are combining the operations. So it just means that instead of passing an integer to a function, getting an integer value as return and giving this integer value to another function, you are moving to the monadic world of the result monad. So you are just wrapping the 11 integer inside the monad here. And when you combine the function, you stay in the monadic world. It means that instead of passing integers from function to functions, you are passing integer result from function to function. And at the end, only at the end, when you want to see if you've got an error or an OK value, you can use pattern matching to deconstruct this monad and come back to the real world. So it is as simple like that. I hope I have explained it simply. So instead of taking an integer and passing it, transforming it with a function to another integer and passing this integer to another function, you just wrap this integer in, for instance, an int option, or it can be an int result, as we have defined before. And you are doing all the operations there from option to option, from option to option. And at the end, you can unwrap it and get back the int that was wrapped inside. Okay, coming back to, I think that it's a good time to do the break. So let's do the break now and come back in 15 minutes.
Sounds good.
Right. So see you in 15 minutes.
See you in 15 minutes.
Hey everyone, coming back from the break. I will share again my screen with the presentation. Okay, great. So we were talking about strong typing. And actually, this is a very nice transition from functional programming to static analysis. And I will explain why. Actually, static typing is some you can say some basic type of static analysis, but it is not so basic. And I would like to show you the power of type systems. With a strong type system, you can do a lot of things. So for instance, if we are talking about OCaml, the main thing is to have type safety. We want to avoid runtime type errors that you may have in other languages. So the types are checked at compile time. And so if you manage to get approval from the type system, so you are pretty sure that you will not have runtime type errors. So also you know the null problem that we have in many languages, and thanks to the powerful type system of OCaml, we don't need to have this null value because we can just use the option type, which is also a monad, but we might say that it is just a type and not a monad. So you just have a type, a very nice type, which is defined with some value or none. And both things are value of the language, and it is not some strange things that you are bringing to your language, like a null value. So you have null safety when you use the option type instead of the null pointers that you might find in other languages. Pattern matching exhaustiveness is also another example that, for instance, when you are implementing a function that will work on a sum type, you can be sure that you didn't forget any case. And when you have a large code base and the definition of your type is actually evolving, so you are changing your type, you are adding one more constructor or removing a constructor and so on. The type system will be very helpful to know, to help you spot all the places that you need to update following your update in the type definition. Immutability is also very important here. And so this is a transition to static analysis, and I would like to show you what we can do with a strong type system. Even a type system that is stronger than what we have in OCaml. Here is a nice video of Ariane 5. We'll not see everything.
By the early hours of the morning of the 4th of June, Ariane 5 stood proudly on ELA 3, waiting for the down over the rocket. There were doubts if it would be able to launch the next day. Its prospects looked poor.
So that is the launch of the rocket. And here, at this point, this is a nice integer overflow.
36.
And so why I want to show you that? Because it is a striking example when a programming error has a huge impact. And this this catastrophe that happened with Ariane 5 could have been avoided with a stronger type system, for instance, or with other methods that will help you to ensure and get mathematical guarantees that you cannot have an integer overflow, for instance, or a buffer overflow, or a division by 0, or any other undefined behaviors that you can have in C, for instance, or in other languages also. And so following this this event with Ariane 5, we have seen a lot of investment in the area of formal methods. So what is formal methods? It is a way to bring mathematical guarantees that your code is correct, that you are not going to have a runtime error that you didn't expect. And so how do you do that? How can you get a mathematical guarantee on your code? So this is some kind of static analysis. And I would like to show you the link between a type system and very high-level static analysis that will give you mathematical guarantees about your code. We have the well-known Curie-Howard isomorphism. What it means is that there is an isomorphism between types and programs on the one side, and theorem and proofs on the other side. It means that if you want to prove something, you can just give an implementation of some function of a given type. So I will show you an example. Here you have a very simple example here on the bottom of the slide. We want to prove that for any alpha and beta, if alpha is true and if beta is true, you have the statement alpha and beta is true also. This is a very simplistic example, but it is to show you how you can use programming in order to prove something like that with a computer. So actually, this can be seen, this logic formula can be seen as a type. For instance, it will be the type quote A, arrow quote B, arrow tuple with A and B. This is how the type would be expressed in OCaml, for instance. So if you want to prove that in OCaml, you can just write this simple function. You are writing here a function, and the type of this function it will be given by the type inference of the compiler, and the type of the function is exactly the logic formula that you wanted to prove. And so you can use this isomorphism in order to prove things about your program. You just need to write, you just need to show that this type is inhabited. If you show an example of a value with that type, it means that the corresponding formula is proved. And so you can go even deeper in the type and have type that are called a dependent type. What is a dependent type? It is a type that depends on value. In most languages, type are living in some world and values are living in another world. And you cannot have a type parameterized by a value. But this is the concept of dependent types, and you have actually languages with dependent type, implementation of dependent type, and it is much more expressive, much more flexible, and still keeping the very strong guarantees that you have from a strong type system. It is an example here. I will not explain all the code, but the idea here is that you can define, you can define here a type. It is a type of sorted list. You cannot define this kind of type in other languages. Even in OCaml, you cannot define that because you don't have dependent types. But here you have the type, define the type of sorted list. All the constructors are ensuring that when you are building the list will always be sorted. And so this is only the definition of the type, but you can define a function, sorted insert, and you can define the sort function. It is just an example of implementation of sort, but the important point here is that when you define that, the compiler, the type system, will check the type, and it will give you the proof that this function will always return a sorted list by type. It is the type system that is giving you this guarantee. And it is a very strong guarantee that you cannot have in most languages. And so, for instance, Coq that I mentioned before is an example of language that has dependent types. And you can do many things here. Interactive proof of properties, proof of programs, and so on. It has a really rich type system, and it is used in practice to implement applications. And for one example here is a compiler, a C compiler that has been entirely written in Coq, and you can run this compiler, but when you give it to the type system, you get the guarantee that the compiler is the behavior of this compiler is correct, is what you expect it to be. And this is done with a very expressive and very powerful type system. And this type system is just one kind of static analysis that we can do. This was for showing you the link that we can have between functional programming, and people of functional programming really care about strong typing, and the next level of strong typing can lead to very powerful static analysis. Another very simple example here, I mentioned when we talked about Lambda calculus that in order to make the Lambda calculus more readable for human, we are defining many syntactic sugar, and OCaml is full of syntactic sugar that compile, that translate into Lambda calculus. And here we have a syntactic sugar. If you look at this, you see that you have a theorem. It is just a logical formula that you want to prove. And behind that, you have a proof of this theorem. And the computer is able to check that the proof is correct for this theorem. But it looks like a theorem and a proof, but in practice, it is not, it is just syntactic sugar. Because the proof is not really a proof, it is a program. Just a syntactic sugar for writing a function. And what the Coq is doing is just taking this function and applying the type system. And the type of this function is that. So when you have a program and its corresponding type, it is exactly the same as having a proof that the logical formula is correct. So now let's come back to the reality. We don't have formal methods, and we are still far from having formal methods available for everyone. It is only a small niche that is used for critical software. But my hope is that in the future, we will benefit from all the important properties that we can have with formal methods, and all the world of static analysis, and bring them into security and into advanced SAST analyzer. For instance, just to mention abstract interpretation, weakest precondition calculus, type inference, and so on. You have a lot of examples like that. And it is a very long way to have very strong guarantees, but I think that we need to dream big in order to reach very high achievements. So this is my hope, and we will come back to concrete things and what we have done in the next parts of the workshop. The next session that we will have in a few weeks. The date is not yet decided, but if you give a like to the corresponding issue, you will be notified when the contest will start. It will actually start next week, and I still need to define when will be the due date to finish the implementation of your chess bot in OCaml. And during the session that we will have in a few weeks, we will do a few things. The first thing will be to do a code review of the code that you have written in order to make everyone learn from each other. And the second thing is that we will do the actual contest. I will write some automation in order to make the battles between your bots, and the best bot will get nice prizes. So it will be fun. Do you have any question? Anything I can answer now? If you have no question, I will just take a few minutes to come back to the examples I wanted to show you previously. So I will share the VS Code. Okay. So we have seen very simple example in OCaml, but I wanted to show a bit more complex things. We have seen in the presentation the definition of the Fibonacci function. So you can see it is a very simple recursive function. Maybe it will be nicer to present it that way. So you have a recursive function taking one argument. If n is less than 2, we just return 1. And if not, we have 2 recursive calls. So it means that it is not tail recursive. So you cannot benefit from the optimization of tail recursive functions. But let's define it. So, okay, this is defined. You can see here that we have the type system that inferred that it is a function from integer to integer. And now we can apply it to 10. We get immediately a result. 20, 30, or 40, it is taking a bit more time. You can see a few seconds actually, and 50. 50, I think that we don't want to wait for the answer. So I will just kill it now. Okay, so why I wanted to show you this function? Because of that. This is the definition of a memo function in order to memorize any possible function. You can see here the type inferred by the type inference. The memo function has this type. Quote it is a function that is taking one argument. The argument is a function itself from quote A to quote B. And when you give this argument, you get back another function from quote A to quote B. So you can see that the type of the parameter is the same as the type of the return value. So what you can see here, I give the Fibonacci function into int, and I get back another function. I can call it also fib. I can call it something else. I get another function which will be also into int. The only difference is that this is kind of a wrapper that is creating a hash table. So you know that hash table is a dirty thing in OCaml. But the nice things here is that this hash table is only local to the function. And from outside the function, you cannot see the difference. The only difference that you will see is the time that it takes to compute the Fibonacci function. So now I have defined the memo function. I am applying memo, and so I'm getting a new fib function, which is now memoized. It means that if I have already applied this function to this argument, I will get immediately the answer from the cache. And so you can see it is the same for most of the, and if you remember for 40, it was taking a few seconds. Let's see. Yeah, it is taking a few seconds. But if I apply it again, I get it immediately. But now let's apply it for 50. And it still takes a lot of time. Why? Because it is a recursive function, and we have memoized only the first call to the recursive function. So in order to resolve this problem, in order to optimize even further, we can define a better memoize function, which is done for recursive function. And as you can see again in the type, it is a very, very generic one. You cannot see here int or string or anything. You can give it a function of any type, and it will return you a function of the same type, but optimized, memoized. So let's do it. And so now I am defining the fib memo by memoizing this function. And okay, applying to 40. And you can see that 40 is already immediate. Even the first call. Why? Because when we have called it before, we have already computed all the calls to 30 and 29 and 28 and so on. And so now if I want to apply it to 50, it will be immediate result also. Just because we have a recursive memoized function. And the important thing here is that it is a very, very generic one, and it is type safe to use it for any type you want. So you have both flexibility and the rigidity of the benefit of a rigid type system. So this is what I wanted to show you now. So if we don't have any further question, I think that we can already wrap up. So thanks a lot, everyone, for joining the session, and keep in touch for the contest. And if we have any question, please leave your question in the relevant issues. I will be very happy to answer them.
Thank you, Mayor. That was great.
Bye-bye.
Thank you, man.